So right now, it's November 2025, and in the last week or so, one of the biggest stories to come out of semiconductors has hit the scene. Seemingly all at once, an unknown startup called Substrate has appeared in top publications, such as the Wall Street Journal, Reuters, and Semi-Analysis, and Stratechery, however you pronounce that. I'm not saying my phone has been off the hook, but suddenly I've got investors chomping at the bit asking me if what Substrate is actually selling makes sense. Or is their story just unobtainable moonshot? This video will strike at the heart of the physics and economics, but won't be the be-all and end-all. We're planning a larger piece over at the More Than More Substack for that. But in this video, I'll take you through what it takes to break barriers in modern-day chip design. Now, I'll say for a lot of these videos, I actually rent a studio. And just as I was coming up to the studio, literally 10 minutes before my time started, the CEO of the company did reach out. I'm still recording this because I think a lot of what I'm saying is still relevant, even regardless of if I speak to the CEO or not. But he is based in San Francisco. I will be there in a few weeks. And so it will be interesting to hear if some of my questions are actually answered. So stay tuned for a follow-up video to this, but it's well worth you at least watch some of this, hopefully to the end, in order to get a sense of why I'm concerned or some of my thoughts on the matter. So it starts with light. At the heart of every chip is a pattern written in light. In order to make chips that we say are built with single-digit nanometer technology, we're talking about lithography, the application of high-powered light onto a piece of silicon to make pretty patterns. Lithography is where that happens, and it's also where most of the money in research and tooling goes. For example, a single modern scanner using extreme ultraviolet light in a leading-edge fab will cost around $150 million to $200 million or more. The tools that shape that light consume more power than an entire city block. Now, as we aim to build chips with smaller and smaller geometries, the numbers define the problem. Today's EUV tools run at a wavelength of 13.5 nanometers, much smaller than you can see, which corresponds to photons carrying about 92 electron volts of energy. Each time you want to use that light, the current chemistry of chip production needs roughly 30 millijoules of energy per square centimeter, or about 2 million billion photons for every square centimeter that gets patterned. That dose, multiplied by 200 wafers an hour and multiple passes on modern transistors, drives the entire throughput and cost model of modern chip manufacturing. Now imagine trying to replace the light, the EUV light of 13.5 nanometers, with what we call soft X-rays. These can be around 1 nanometer wavelength, and depending on where in the scale you point at, these light photons carry anywhere from 2 to 100 times more energy each. In principle, this should enable a finer pitch of lines drawn in silicon. In practice, it changes everything else. The mirrors we use to stop reflecting, the chemical interfaces we use to make patterns stop responding, and the light penetrates deeper instead of stopping near the surface. And that energy budget jumps from tens of watts to kilowatts. The equation that we've used to make EUV economical no longer applies here. And this question as to whether X-ray lithography could ever replace EUV has come back into the focus because of new claims from companies like Substrate. This Peter Thiel-backed startup suggests X-ray exposure could leapfrog the existing process entirely. If true, that would be one of the biggest shifts in semiconductor history, bigger than the shift to EUV itself. It's a lofty goal that has many people in this industry on board, but the physics, the engineering, and the economics all tell of a harder story that needs solving. In this video, I'm going to go some way to unpack that story. We'll start with what electromagnetic radiation actually is, and how the wavelength, frequency, and photon energy are all linked. We will look inside the fab to see where the lithography sits among the major process steps, from deposition to metrology, and why the lithography step dominates the cost. Then we'll go deep into the physics, how EUV light is made, what makes X-rays different, and why the statistics of photons, using terms like shot noise and stochastic variation, to show that there are hard limits that no amount of optimism can erase. Finally, I want to just address the economics of fabs, the cost of X-ray production, and the human story behind the current publicity wave. If you're interested, stay for the whole video because it's going to be a wild ride, and there'll be some numbers and explanations. If you like this content, there are multiple ways to support the channel. You can like and subscribe this video, and many thanks for doing so. There's also Patreon, which gives you access to our Discord. There's a merchandise store and a newsletter, links in the description. For all of you who do contribute, thank you. You are keeping me well fed. So before we compare EUV and X-rays, let's actually just remind ourselves what light actually is. Every form of illumination we use in semiconductor manufacturing, from deep ultraviolet to X-rays, belongs to the same spectrum of what's called electromagnetic radiation, or EM. Because visible light is in this spectrum, we often use the word light to mean all of the spectrum. That means all the way from radio waves to gamma waves. So I'll say light a lot, even when referring to X-rays. The only difference between these sections of light is wavelength. And to remember that wavelength, frequency, and the energy carried are all interlinked. We're also going to talk about photons, which in essence are light particles of energy. I won't get into the physics of waves versus particles, but in chip design we talk about photons of light with a wavelength. So what exactly is light? When we talk about electromagnetic radiation, we're describing two complementary things. Light is a combination of an oscillating electric field and an oscillating magnetic field that moves through space. The fact that it's two fields isn't really important to this story, but the thing is that this light travels in the speed of light in a vacuum. The wavelength of this light is directly proportional to the frequency, and the frequency of those oscillations determine how energetic each photon of light is. The relationship can be described in one line. Energy equals a constant times the speed of light divided by the wavelength. Now that constant is called Planck's constant, and that makes the entire top line of this equation a constant. In other words, that means if we shorten the wavelength of light, it means we have a higher frequency, and a higher frequency means that each photon carries more energy. In the spectrum of light, we have meters to picometers here. And for visible light, the wavelengths run from around 700 nanometers for reds to 400 nanometers for blue and violet. This ultraviolet light region, all of it, sits below those numbers, from around 10 to 400 nanometers. It's in this region that we use light to manufacture chips. 248 nanometers, 193 nanometers, and a couple of others over the years. Beyond that region comes extreme ultraviolet light, and the light used in today's most advanced lithography tools is at 13.5 nanometers. Going further below that is into the X-ray region, although the boundary between the two, the sort of single-digit nanometers, is what we call X-rays. Now, fun fact, EUV lithography was originally called soft X-ray lithography in the literature in the 80s, before they narrowed in on exactly 13.5 nanometers and started calling it EUV. The thing is, as you go down that spectrum, the behavior of light begins to change. We're talking about how the light reflects off surfaces or how it can be focused by lenses. For example, in order to reflect ultraviolet photons, mirrors need special coatings to reflect properly. EUV already requires a vacuum environment and a complex stack of mirrors made from advanced chemistry and years of research. For example, in here, alternating molybdenum and silicon layers. Each reflection loses around 30% of the light power. Once we move to X-rays, for example, those mirrors stop reflecting efficiently altogether because the photons are just simply too energetic. They penetrate the mirrors rather than bounce off them. That transition from reflection to absorption is not just an optical issue. It defines the economics of lithography. When mirrors lose efficiency, you need a brighter source to deliver the same number of photons to the wafer. A brighter light of X-ray source means higher power, more heat, and more cost. This is why the relationship between wavelength and energy is so important. It's not just a physics equation, it's the line that separates what can be manufactured with modern tools from what cannot. Now, just to give some numbers here to start, in EUV, each photon carries around 92 electron volts of energy. An electron volt is just simply a unit of energy, and in this case it helps us understand the scale. In the soft X-ray range, each photon can carry from 200 to over 1,000 electron volts, depending on the exact wavelength and frequency. It means that each photon hits 2 to 10 times as hard or more, and needs more power to produce. That jump makes the light harder to handle. It also changes how light interacts with materials. Instead of stopping near the surface when you interact with a silicon wafer, it can pass through, or interacts deeper, spreading the energy deeper and wider. We'll talk about why this becomes a problem later, but the key point here is that by moving to shorter wavelengths, you are trading more energy per photon for less traditional control over where that energy lands. To understand why light plays such a central role in chip making, we need to actually look at how a chip is built. A modern finished processor may have tens of billions of transistors, or an older one might only have a couple million, but at the level of the fab, it's just a repeating cycle of adding, shaping, and polishing thin films of material until an electrical circuit appears. A modern wafer will go through hundreds of individual steps, but a lot of them are repeated. These steps all fall into about 20 rough categories, but rather than go through each of the 20, let's just walk through a small-scale example of how the pattern of light is used and why lithography dominates that cost. Let's start with a bare wafer. We create wafers by growing silicon ingots from crystals, cutting them and polishing them so flat that the surface height varies by less than a nanometer edge to edge. There are companies dedicated to this, and some designs use specific silicon orientations or coatings for certain properties. The fab doesn't create these, they buy them in depending on the design. Now, with that wafer, the first thing we do is grow or deposit a thin silicon oxide layer on the surface. That oxide acts as an electrical insulator to the bulk silicon, and the clean base to build transistors into and circuits on top of. It's formed by heating the wafer in an oxygen-rich environment, where the silicon reacts with the oxygen to form silicon dioxide. This forms also a stress buffer. It keeps later layers of special elements from diffusing through into the bulk silicon base, and helps prevent contamination. Once we have this layer, next is isolation, or carving out regions where transistors in our chip will be and separate them from one another so that they don't interfere. This process is called shallow trench isolation, which sounds complicated but starts with depositing a protective layer for the oxide, known as a hard mask. This is there to help the next steps where we deposit a layer of photoresist. The photoresist is what helps create the patterns to build transistors or pathways. You spin a thin layer onto a wafer, and either leave it as a semi-stable liquid or harden it to a solid layer through heating. Then we get to the main part, lithography. By using a mask, basically a stencil, we use light on exposed areas of the photoresist. If the photoresist on the wafer is liquid, on the areas you expose it to, it hardens. If the photoresist on the wafer is a solid, then the areas you expose will become a liquid. The idea is that you're left with regions that can form the basis of your transistor design. The next stage is chemical mechanical polarization, or CMP, which polishes the surface back to a smooth, even layer. The technology of CMP is so cool. We can polish a wafer down to the nanometer and sometimes even down to the atom with physical processes. Think of it like fancy, tiny polishing. This defines the neighborhood boundaries for each future transistor and makes the wafer perfectly flat for the next operation. Those regions are now etched down into the silicon using acids and chemicals that can etch silicon oxide but leave the photoresist in place. These types of acids, or etchants, matter here, and they determine how deep the regions are and the profile. For example, some of these etchants are very predictable about their rate of etching, and some only etch in one plane of the crystal lattice. Now we define the electrical personality of those etched regions. Using ion doping, we shoot atoms of various elements into the silicon oxide in exposed areas. These dopants will set whether the region will conduct with electrons or with holes. A high temperature cooking / annealing step then follows to help activate those dopants, reacting them with the oxide lattice. It also helps repair damage from the ion beam. Each one of these steps needs its own mask, and each mask must line up exactly with the layer beneath it to picometer level accuracy. With the transistor area defined, we move on to the stack that sits on top, the first part that helps control the transistor, and then the power and connectivity. The stack is different for planar transistors compared to FinFET or gate-all-around transistors, but for simplicity here, I'll just stick to planar. First, we start off by depositing a thin dielectric material, often using a process called atomic layer deposition. This grows up to just one atomic layer at a time. This forms the insulating barrier that separates the channel, which we just built, from the gate on top. On top of that, we deposit the metal gate material, typically by physical or chemical vapor deposition, at several dozens of nanometers. Then we coat the wafer, again with a photoresist, and use lithography to define the gate pattern. The unwanted metal is etched away, leaving behind narrow strips that will form the transistor gates. The characteristics of the gates define the transistor performance, so this step typically defines the node size. After etching the gates, we deposit a thin layer of nitride and perform a unidirectional etch, that's compared to an anisotropic etch, to spacers around the gate. These spacers control how far dopants can spread during later implants and help shape the electric field around the channel. Then come more ion doping to form the parts of the transistor that actually carry the current. Another rapid anneal step activates those dopants, and by now we've built a working transistor. It's still buried in that initial oxide layer and not connected to anything. So the next step is to make contact points so the transistors can talk to each other. We deposit a thick insulating dielectric layer to isolate the gates and channels, and use lithography to open small holes, called contact vias, wherever we want to connect the transistors. These holes are etched down through the dielectric until they reach the transistor's source, drain, and gate material. Then they align with a barrier filled by chemical vapor deposition and polished flat again. These plugs act like vertical wires that link each of the transistors up to the metal layer above. This is when we can start building the wiring, the interconnect. First layer, known as metal 1, is formed by depositing a dielectric film to reduce capacitance, apply your photoresist, and then use lithography again to define where the wires and vias go. Plasma etching then cuts those paths into the dielectric. A thin barrier and seed layer are added, then copper is electroplated to fill the trenches. Polishing removes the excess copper and leaves the surface smooth again. Metal 1 carries the densest local wiring between transistors, and its pitch is among the tightest on the chip. We then move to higher layers like metal 2, metal 3 and metal 4 and so on. The lines become thicker and further apart, carry larger currents and connect longer distances across the die. Every one of those metal layers requires multiple lithography steps, several depositions, etches and planarizations. And after each layer, tools are used to check that the pattern is within nanometer tolerances in a process called metrology. Even the polish endpoint is determined by monitoring reflected light intensity on the polished layer and enables the system to see changes as layers become flat. Optical inspection and scatterometry are used constantly to detect defects and verify alignment. So while lithography is important, light is used all around the fab to check, correct and control the process at every step. When that top metal layer is done, we add a passivation layer, sort of like a protective layer of silicon oxide and nitride films that seals the chip from moisture and contamination. Then we use lithography again to open small windows through that layer for the bond pads that connect the chip to the outside world. After that, wafers can be thinned, cut and made into individual chips and then sent to packaging to get into the hardware we're normally familiar with. Through all these stages, the same core pattern repeats. Deposit a layer, use light to define a shape, etch or implant where the light tells you, then polish the surface flat before doing it again. That repetition is what makes lithography so central. We use it more than once, and it's the heartbeat of the entire manufacturing loop. At the lowest layers, we need the best tools to define the smallest features, and that's why lithography, the part that's powered by electromagnetic radiation, dominates both the cost and complexity of chip making. And this is a context that makes the promise of X-ray lithography so striking. If someone says they can replace the most expensive part of this chain with something smaller, faster and cheaper, they're talking about rewriting the economics of the entire fab. Now let's talk specifically about that lithography step. Every time we want to define a new pattern on the wafer, we use the lithography tool, which we also call a scanner. The scanner's job is to take the pattern on a mask and project it onto the wafer using light at a very specific wavelength. The whole process is enabled by the simple fact that the shorter the wavelength of light, the smaller a pattern can be printed. That's a whole reason we've gone from visible light to deep ultraviolet and now to extreme ultraviolet at 13.5 nanometers. Inside each scanner is a complex optical chain designed to control that light. For EUV, that chain is entirely reflective. The light from the source hits a mirror called the collector mirror, and it bounces through a series of intermediate optics to pass through the photomask. And it's finally put down onto the wafer afterwards. There are no lenses. Every surface is a mirror made out of alternating layers of molybdenum and silicon. These mirrors were specifically developed due to the characteristics of EUV light. You need a mirror that reflects as much as possible. And even with the best architects in the business, due to simply physics of high-energy photons, each mirror that we use today only reflects about 70% of the light that hits it. That means after a dozen bounces, barely a few percent of the original light left makes it to the wafer. And that's why the EUV light source, which is actually firing lasers at a tin plasma, has to produce tens of watts of in-band radiation just to keep throughput high enough. The losses on the source are crazy too. Hundreds of kilowatts just create tens of watts of in-band radiation. So when looking at the tool as a whole, the manufacturing process from an economic standpoint, once it's installed and up and running, throughput is everything. Each wafer has to be exposed, developed, and moved out of the tool in seconds, not hours. Due to the optics, a modern EUV scanner can expose field roughly 800 square millimeters at a time. Then it has to expose that across the entire wafer. It's about 64 to 80 dies. A modern EUV scanner handles around 150 to 200 wafers per hour. If you do the maths on that, that means each wafer spends about 22 seconds being exposed. 80 exposures in 22 seconds means that each exposure is about a quarter of a second, or less than, because the system has to move the wafer around during that time. Now it's fast, but it's only possible because every part of that optical and mechanical system has been tuned to handle the physics. Now it also comes down to how much you actually want to expose the wafer to the light. The more you expose the wafer, the better your transistor design is defined, but the longer time it takes and the slower your throughput. There are secondary side effects with longer exposures too, most of them negative, so it makes sense to try and process the wafer as quickly as possible while still getting that design down on your chip. ASML is the company that makes these EUV scanners. It's the only one, and often quotes wafer throughput at a specific dose of light. This is the 30 millijoules of light energy I said at the beginning, 30 millijoules per square centimetre of silicon wafer. Now, in the early days of EUV, I heard companies were using up to 80 millijoules per square centimetre. But most of the leading edge fabs today are agreeing that 30 or so is the right number for the wafers per hour metric. The point being is that more exposure time means slower throughput, and every second adds up across hundreds of wafers, reducing overall profitability. Now, a little bit about metrology here, because light also appears in all the places you might not think about. When we check how accurately one layer aligns with another, we use visible or deep ultraviolet lasers to overlay in that metrology. We use them to measure film thickness or the roughness of a polished surface. For that, we use ellipsometers, instruments that shine light at precise angles and analyze the reflected polarization to nanometer level accuracy. When we search for particles or defects, optical inspection tools scan the wafer with bright lasers and look for scattered light. Even the plasma etch tools use electromagnetic radiation indirectly. They rely on radio frequency power to generate and sustain the plasma that etches the wafer. Electromagnetic radiation and light just simply isn't only in the lithography tool. It's woven into the chip production workflow and metrology as well. But it's the part that costs the most money, by far, is the lithography itself. The reason is simple. Resolution costs exponentially more as wavelength gets shorter. To work at 13.5 nanometers, you need a full vacuum system, a tin plasma source that can fire at tens of kilohertz, a pellicle membrane that can survive those power levels, and mirrors polished so precisely that a single atomic bump would ruin the focus. Each of those subsystems is its own research program, with more than 100,000 people working on it. The laser source, for example, and the act of firing CO2 beams at tin droplets to create usable EUV light is an engineering feat that took 2 decades to refine and get to power levels suitable. The optics inside the scanner are produced in controlled environments by only a handful of suppliers worldwide. The mirrors are so sensitive that a stray particle would destroy them, so the entire optical path is sealed in vacuum chambers, constantly monitored for contamination. Then you have the system that moves the wafers inside the machine as they're being exposed, which must move the wafer under the beam within nanometer precision at accelerations that would crush anything human-sized. When you add all of that together, a single EUV scanner ends up costing more than a passenger jet. And even then, it needs maintenance, calibration, and a resupply of consumables. The operating cost alone of a single machine can run into millions of dollars per year. And that's why when somebody proposes to replace EUV with something new, like X-ray lithography, well, one intermediate question is if the physics works, another is if the economics do. Every photon that reaches the wafer has to already cost a fortune to generate, transport, and then control. The shorter the wavelength, the higher the photon energy, and the harder it becomes to control that photon and use it where you want it. So let's go back to the photon generation in lithography. As mentioned, the physics of generating extreme ultraviolet light is already difficult. Generating X-rays suitable for chip making is something else entirely. The methods share the same basic principle though. Accelerate particles, make them collide or bend, and capture the radiation that comes out. Problem is that the energy scales very quickly, and engineering challenges grow by orders of magnitude as we move from EUV to X-ray. Let's start with EUV. To get 13.5 nanometer light, you can't just use a laser or an LED like we used to use the previous methods. There's no material that can actually emit or amplify at that wavelength in a normal situation. Instead, we make the light indirectly. We create a plasma so hot that its electrons radiate at the right frequency. In an EUV machine, in an EUV scanner, a carbon dioxide laser fires at droplets of molten tin. These droplets are about 30 microns across. And the way the molten tin is actually created in the machine itself is really interesting. I've gone into it. It could be a topic for another video. And the fact that it's now a continuous feed system, you used to actually just have to put ingots in there. The thing is, each tin droplet that it gets fired out gets hit by a laser twice. The first laser pulse flattens it into a disk, and the second vaporizes it into a plasma. Now that plasma is really hot, with temperatures above 200,000 Kelvin. At those temperatures, the tin atoms are stripped of many of their electrons, and as they cool, they recombine. That recombination emits a spectrum of wideband light. The spectrum has emission lines though, like the sodium lamp emission lines if you're familiar. The trick is that one of those emission lines sits conveniently around 13.5 nanometers, right in the EUV region. Now one problem here is that if you're just firing lasers at tin, the radiation goes in every direction. So we use that mirror called the collector to gather it. The collector is a multi-layer optic shaped like a nested dish, designed to focus as much of that in-band light as possible into a beam that can be directed into the lithography system. Now we have to make sure that the collector doesn't end up with molten tin splattered across it, reducing its effectiveness. Now even after all of that, the efficiency is tiny. The carbon dioxide laser draws hundreds of kilowatts of electrical power, but by the time you have usable in-band EUV at the intermediate focus, you might have 10 to 20 watts left. Now let's pivot on how we do that with X-rays. To make a 1 nanometer photon, for example, we need electron energies a lot higher, and there are a few ways to do that. The simplest is the Bremsstrahlung method, where you fire high energy electrons into a metal target and collect the X-rays that come out when the electrons decelerate. That's how medical X-ray tubes work. But this method produces a broad continuous spectrum, perfect for an X-ray image, but not the narrow band we need for lithography. It would be like trying to print a fine pattern with a flashlight instead of a laser pointer. To get narrow, tunable X-rays, you need what's called a synchrotron, or a free electron laser. These machines accelerate electrons to near the speed of light and then bend them with magnetic fields, kind of like the Large Hadron Collider, but just a bit smaller. When charged particles like electrons bend, they emit radiation, and if you do it repeatedly in a controlled lattice of magnets called an undulator, you get coherent X-rays. The wavelengths are determined by the electron energy and the spacing of the magnets, and you can tune those parameters to generate anything from soft to hard X-rays. That radiation is strong, directional, and, in research facilities, perfect for tools like microscopy and spectroscopy. So let's ask the question, what about for lithography? So let's start with the building. Let's do a comparison here. A synchrotron is a ring, and in order to use the light, you need to build what's called a beamline. Modern synchrotrons might have a dozen beam lines at various parts around the ring, but if needed at higher density, you could probably build 30 or more. Each beam line sits at a point where it gets the same electromagnetic spectrum, but with particular optics, you can narrow it down to what's needed with precision. As a result, each beamline footprint is hundreds of meters. Power draw for the whole system is in tens of megawatts, and you can't easily turn it on and off between wafers. The concept of free electron lasers push coherence even further, but they require superconducting linacs, cryogenics, and vacuum bead pipes hundreds of meters long. Ultimately, these are both sorts of billion-dollar research facilities. They're not something you can install next to a clean room or run in shifts. The thing is, one of the arguments is that this is okay given the cost of EUV machines. But the scale difference is what separates EUV from X-ray. In EUV, we already have to compress a laser-based fusion experiment into a 2-meter wide light source, and that alone took 2 decades of development. To go shorter in wavelength, we need to move from tabletop lasers to particle accelerators, and that's not an incremental change, it's a change of regime. There's also the question of brightness. A lithography scanner doesn't need photons, it needs many photons, concentrated into a beam the size of a reticle field, which, as I said before, today sits around 800 square millimeters. That beam needs to provide 30 millijoules of energy per square centimeter in a fraction of a second. Synchrotron sources can deliver brilliant beams, but most of that brightness is focused into millimeter or micron-sized spots for scientific experiments. It's simply a problem of photons, which we'll get into a bit. So now that we've covered how EUV and X-rays are made, we can talk about how they're used to actually make patterns, because producing the photons is only half the problem. The other half is turning those photons into shapes on silicon, and that comes down to how we handle the light between the source and the wafer. So in modern chip making, we have something called a mask. Think of it like a stencil, but it's much more complicated, and there's a whole segment of the industry designed to optimize the stencil patterns for the smallest features. The mask, or sometimes called the pellicle, carries the circuit pattern we want to print on the wafer. Now, light can either pass through the stencil or it reflects off to provide the pattern. The scanner's optics shrink what went through and then project it onto the wafer below. For previous lithography, before EUV, the process used what's called transmissive optics. Light passes through a glass photo mask with opaque features. For EUV though, that's impossible. There's no glass that allows EUV light to pass through. So as a result, EUV masks are reflective, just like the mirrors inside the scanner. They're made from layers that reflect 13.5 nanometer light at a specific angle. The top of the mask is then patterned with an absorber layer that blocks the EUV where we don't want it to reflect. Now, every one of those layers on the mask has to be nearly perfect. A defect in any layer in the multi-layer stack can distort the reflected light, and a particle landing on the surface can project as missing or extra features onto the wafer. That's why mask inspection is such an important and massive part of the EUV ecosystem. Companies spend enormous resources checking and repairing reticles because a single defect in that mask can ruin hundreds of wafers before it's even caught. Now, there's also a concept here of maskless lithography. The idea that instead of using a physical mask, use a programmable pattern generator on the light and simply control the mirrors to write the pattern. In theory, this means no masks to make, no defects to propagate, and full flexibility for each exposure. In practice, it comes down to speed. A mask projects an entire field at once, whereas a maskless system has to draw it point by point, which is orders of magnitude slower. Even the most advanced electron beam writers, which is another field in itself, can't keep up with production throughput. E-beam scanners, for example, are maskless and can create super small features. They're brilliant for making masks in the first place, or doing rapid prototyping, but not for patterning thousands of wafers per day. For X-rays though, the problem is even worse than all of that. At single-digit nanometer wavelengths, traditional reflective masks don't work. The photons are too energetic and pass straight through most materials. Transmissive masks don't work either because the substrate would absorb or scatter too much of the beam. That leaves only two options: proximity masks, where the mask sits just a few microns above the wafer, or direct-to-right systems where there's no mask at all. Proximity masks were tried in early X-ray lithography experiments by IBM and others a couple of decades ago, but they create new issues. Any tiny vibrational particle changes the distance between the mask and the wafer, blurring that pattern. Even a truck driving outside can disturb the design. The membranes used for these masks, usually made from silicon nitride, are also fairly fragile, and the pressure differences from exposure can distort them. They also collect contamination from being so close to the wafer that quickly reduces throughput. That's why proximity lithography never scaled beyond research. Direct to right with X-rays avoids those masks entirely, but then you're drawing every feature individually. It's kind of like painting the Mona Lisa with a needle 1 pixel at a time. You could, in principle, expose a field using a focused microbeam that scans across the wafer, but the photon flux needed to cover even a small die in a reasonable time is astronomical. Even with the brightest X-ray sources we have, writing one chip could take hours. It's perfect for nanofabrication in the lab, but not for a fab that runs 24/7. And there's one technique here also that does come up: imprint lithography. Instead of using light to define a pattern, you could just simply print it on, using a mold and a resist that cures it. You're not projecting photons, you're just stamping. It sidesteps all the optics, and in theory can reach atomic scale, but the issue is purely mechanical. The challenge is alignment and defect control. Every time you press into the mold, into the resist, particles or small deformations can damage the pattern. The mold itself wears out quickly, and cleaning it without introducing defects is a nightmare. Imprint lithography has seen successes in applications like NAND flash. I think it's either Canon or Nikon that are pushing it hard. Every so often we see a paper in Nature about it that gets picked up by the press, who can't read the graphs properly. But it struggles for the varied and precise layers used in logic chips. So in practice, every path, every type here that avoids a traditional mask has its own bottleneck: speed, precision, or durability. Every path that keeps the mask runs into the problem of how you handle ever shorter wavelengths of light. That's why, even after decades of research, projection lithography with masks still remains the standard. It's the only method that balances speed, resolution, and repeatability at scale. Now from that, let's go on to how the X-rays actually interact with the wafer. Even if you could build the perfect X-ray light source, even if you had the brightest beamline and the cleanest optics in the world and sorted out the stenciling, the movement the moment these photons hit the wafer, the physics stop being your friend.
Computer says no.
Lithography at these energies ends up being limited by those statistics, by how light and matter behave when things get really small. Now it's worth noting here that some of the issues I will bring up were originally brought up when we had EUV, and when that was still in the design phase, but they were solved over time, or in some cases are still being worked out to provide better throughput. The questions, however, are still being asked on the X-ray side extensively. Now, at the scales we're talking about, every photon of light matters. In EUV lithography, we already know that we need around 30 millijoules per square centimeter to expose a photoresist properly. If you convert that into actual numbers of photons, that's roughly 2 million billion photons per square centimeter, or 2 times 10 to the 15. It sounds like a lot, but for features only a few dozen nanometers wide, that translates to a few hundred photons per feature, and that's before accounting for how light interacts with the resist and the wafer. Now let's start with randomness. Even though we focus these photons into a field the size of a reticle, there is still randomness in how the photons move. The randomness of how those photons arrive and interact is what we call shot noise. It's a statistical property of light, and we describe it by the square root of the number of photons that arrive in a feature. So in plain language, that means the fewer photons you have, the greater your percentage of variation, and this is often seen as fuzzy edges around the side of the features. If a pattern requires 1,000 photons to form, the variation from shot noise alone is around 3%. But if you only have 100 photons, that variation jumps to 10%. For something like a transistor gate, 10% is the difference between it working and not working. As we move from EUV and that 92 electron volts of energy per photon to soft X-rays, which has several hundred to even 1,000 electron volts, the number of photons needed to deliver the same energy dose, assuming the same absorption, drops dramatically by up to an order of magnitude. Because each photon carries more energy, we need fewer of them. And because shot noise gets better with more photons, it means with fewer photons, it gets worse. You can try to increase the dose to compensate, but that slows the process, heats the photoresist, and risks damaging the wafer underneath. Now we also have the stochastic variation of the chemistry here, and this is what happens after the photons hit the photoresist and the wafer. When an EUV photon hits a resist molecule, it doesn't just break one bond to form the polymer. It releases a cascade of secondary electrons that spreads the energy around. And that's how you get a pattern. The photons change the resist chemistry, which then develops differently in the exposed and unexposed regions. But because the number of and direction of those electrons are random, every exposure is slightly different. These are the missing holes or bridge defects that have haunted EUV since its early development. They happen because sometimes a few too many or too few secondary electrons hit a certain critical spot. Again, if you need more photons, the problem is solved by statistics. Now with X-rays, it gets much worse because you need fewer photons. Each photon carries so much energy as well that it carries a deeper, broader electron shower, with each secondary electron traveling tens or hundreds of nanometers through the resist, or even into the substrate below. Instead of a localized reaction, which is what you want, you get a three-dimensional blur of energy. The very thing that makes X-rays powerful, their penetration, makes them terrible for surface patterning. You're not exposing a thin film anymore, you're literally bombarding the wafer. And penetration depth is one of the biggest unsolved issues. Higher energy photons travel further through an object before being absorbed. EUV photons are absorbed within the top few tens of nanometers of the resist, which was an initial problem when it was being developed, but the design chain has adapted. X-rays at 1 nanometer wavelength, by contrast, can pass through the resist. The resist would need to be thicker to absorb them, but a thicker resist introduces new problems: less focus precision, more line edge roughness, and a greater aspect ratio collapse during etching. Every fix introduces a new failure mode. Now what about the absorption materials chemistry of the resist itself? EUV resists are an exotic blend of carbon, oxygen, and metallic compounds designed to absorb just enough of that 13.5 nanometer light to react, without overdoing it. These compounds then react to provide the lithography chemistry that's needed. They've been tuned over decades. At X-ray wavelengths, those materials actually barely interact. You need elements like tin or gold embedded in the resist to capture the photons effectively, but those same elements cause scattering and secondary reactions that blur the pattern even more. This means that there's a practical chemistry problem. The resists we use today interact cleanly under EUV doses and within design limits of heating and such. With X-rays, the energy is high enough to break everything apart violently. You don't get neat photoacid reactions, you get carbonization and bubbling. The result means a breakdown failure of the chemical itself. It isn't a crisp chemical gradient, it's just simply damage. Researchers have tried metallic and inorganic resists to withstand it, but those require etch processes that don't integrate well with existing fab chemistry. Even if you could solve the chemistry, you still have the heat. When each X-ray photon carries hundreds of electron volts, it would mean you're dumping kilowatts of power into a wafer surface that it can't dissipate evenly. EUV uses optics to help deal with this. X-ray doesn't have that luxury. Local hotspots can build up, leading to warping of either photoresist or the wafer. You could reduce the beam intensity and scan more slowly, but then throughput collapses, which breaks the economics. All of these effects, the shot noise, the stochastic spread, the deep penetration, the low absorption, and the thermal load, all stack on top of one another. Fixing one usually worsens another, and it's an incredible problem to solve, which is why the big companies have already tried. Let's talk about that previous research and how most of it's already public, but we have to go back to the 70s. So long before EUV was ever shipped in a scanner, X-ray lithography was the greatest hope of the semiconductor industry. The idea dates back to the 1970s, where companies like IBM and Bell Labs, and then later Toshiba and Hitachi, and others, believed that using shorter wavelengths could extend Moore's law indefinitely. They were already hitting the limits of ultraviolet optics at the time, and it seemed natural that X-rays, sitting a few orders of magnitude below visible light, would offer the resolution to keep shrinking transistors for decades. The theory itself looked perfect on paper. IBM's researchers in the late 70s demonstrated sub-100 nanometer lines using soft X-rays at 1 or 2 nanometers in wavelength, well below EUV that's used today. These experiments were done on synchrotron beamlines, the same kind of machine still used today for materials research. And the results today were stunning. Perfect, sharp lines, atomic level resolution, and potential alignment precision that conventional optics at the time couldn't match. The thing is, they also used 4-inch wafers, which was standard. At the time, there were serious proposals to commercialize it, and even government-backed research programs in the United States and Japan to explore whether synchrotrons could be adapted into lithography tools. But the problems appeared as soon as people tried to scale it beyond the lab. The issues we've discussed, such as shot noise, resist chemistry, and mask fragility, showed up immediately. The exposure times were too long, the resists decomposed under high energy bombardment, and the masks failed after only a small handful of wafers. Even the best results still required proximity printing, with the mask suspended just microns above the wafer. Any vibration, thermal expansion, or mechanical drift ruined the pattern. IBM actually built dedicated X-ray beamlines in the 1980s, specifically for lithography trials, often using synchrotrons at Brookhaven National Lab and other facilities. They published hundreds of papers on membrane masks, gold absorber layers, and new resist chemistries like PMMA derivatives. They achieved line widths below 50 nanometers, long before EUV ever existed, but never with enough consistency to make a chip. The problem wasn't making just one pattern work, that was fairly easy. It was making a few million of them in the same place on every wafer. And today we need a few billion of them on every chip on every wafer. By the mid-1990s, X-ray lithography had reached what IBM called an engineering wall. The X-ray sources were too large, the optics were too complex, and the masks were too fragile. A single synchrotron beamline could expose one small 4-inch wafer every few minutes, or the equivalent of a modern 300mm wafer today in about 24 hours. It was nowhere near the hundreds per day needed for mass production, or even the dozens per day for the leading edge at the time experimental work. The economics simply couldn't work. Meanwhile, deep ultraviolet tools using 248nm and later 193nm light were progressing rapidly thanks to lasers and photoresists that could be tuned for each generation. Those systems were smaller, faster, and compatible with the existing fabs. When EUV research hit the ground properly in the early 2000s, it borrowed heavily from those earlier X-ray studies. In fact, EUV for a long time was called soft X-ray. Many of the same scientists were involved, especially at IBM and the national labs. The key insight here was that EUV at 13.5nm was short enough to print fine features, but still long enough that mirror optics could reflect it and photoresists could absorb without destruction. In other words, EUV found a practical middle ground, short enough for resolution, long enough for engineering. Now, the research on X-ray lithography never really stopped. It just changed purpose. Synchrotrons and free electron lasers became the tools of nanolithography research, materials imaging, and protein crystallography, not for manufacturing chips. By the 2010s, EUV had taken over as the only plausible next step, and almost every major lab shuttered or redirected its X-ray lithography programs. Now, with Substrate, the company I'm supposed to be talking about, and a few others resurfacing the concept, the question isn't whether X-rays can make those fine features, because we already know from all that research they can. It's whether they can make those features reproducibly, economically, and within the thermal and chemical limits of modern wafers. Every company that's tried before ran into the same wall. The numbers just don't scale. The industry didn't abandon X-rays because they failed scientifically, it abandoned them because they failed economically, and it always comes down to economics. So let's turn to the company for a second here. It burst into view at the end of October 2025, launching with simultaneous coverage across high-profile websites like Bloomberg, Wall Street Journal, Stratechery, SemiAnalysis, and they themselves had a slick website promising nothing less than a revolution in chip manufacturing. A return to leading the world with semiconductor manufacturing for America! The headline claim is simple. Substrate says it has built a practical X-ray lithography platform and intends to use it to power a new American foundry capable of making sub-2nm chips at half the cost or less of today's leading fabs. The company itself is based in the Bay Area and backed by Peter Thiel and his Founders Fund, alongside a number of smaller venture investors, and has raised over $100 million in early funding. That sounds large until you remember that a single EUV scanner costs twice that. The money, according to CEO James Proud, has already been spent building prototypes and accelerator infrastructure, though as far as we're aware, no one outside the company has seen a working tool yet. There are some images from Reuters, but as explained by other lithography experts, these clean rooms look way too small to be substantive use for this endeavor. Proud himself is actually an unusual figure to be leading a lithography startup. He has no practical lithography or semiconductor background, or not even a degree, let alone a STEM one. He's a Thiel Fellow who moved from the US to the UK and has since become a US citizen. Proud first gained attention for Hello, a consumer electronics startup that created a smart sleep tracker, a product that technically shipped but collapsed within a couple of years, and the IP was sold to Fitbit and then ultimately to Google. He later founded a company called Config, a software platform for hardware development management. Substrate is his most ambitious venture yet, and he often frames it in ideological terms, a mission to save American manufacturing and restore national technological leadership and prove this is what the US can do when it sets its mind to it. It's a narrative that permeates all the discussion of marketing, almost to the point of ignoring actual questions. The thing is, that framing is no accident. The language echoes the Thiel Fellowship's long-standing themes of individual audacity and national revival. As with other Thiel-backed projects, such as Palantir, Anduril, and even the crypto initiatives that promise to restore Western sovereignty, Substrate wraps a technical proposition in patriotic urgency. Every interview that we've seen reinforces the same line, that the United States invented almost every major semiconductor technology and that its dependence on Taiwan represents a national vulnerability. Now that's not entirely wrong for sure, but the angle that this is the way to save it verges on this is the only way to save it, and the default answer is anything. The default answer to anything has caused a lot of concern. Now, the announcement itself was engineered for maximum impact. The company claimed to have measurable performance metrics rivaling or exceeding high-NA EUV, such as single patterning capacity for all layers down to 1 nanometer, 12 nanometer features demonstrated, an overlay below 1.6 nanometers with line edge roughness below 1 nanometer, and 50% lower cost per wafer compared to existing foundries. Now, if true, these numbers would overturn every assumption about X-ray lithography economics. But as with all extraordinary claims, it requires extraordinary evidence. And right now, there is no corresponding data. Now, there are images of supposed lithography lines, but no scale on those images. There's no detail in terms of dose curves, no resist specifications, no wafer maps, no uniformity plots, and no optical designs. The company has not disclosed its operating wavelength or photon energy, which are essential to verify any X-ray process. The core technical story here is that Substrate uses a particle accelerator-based light source derived from research at US national labs. The CEO says that this generative accelerator source can produce a bright continuous beam of soft X-rays without requiring a full synchrotron complex. The idea is to amortize one large accelerator across many exposure tools, effectively turning a national lab beam line into a factory service. The argument here is that also the cost of such a facility is in line with modern EUV costs. If you put 20 EUV machines in a big fab, that costs a few $1 billion. That could build one of these machines or a synchrotron. But even with the interview at Stochastic, physics questions remained unanswered. When pressed, CEO James Proud declined to provide figures to avoid giving a blueprint to other countries. There's no mention of chemistry or how the company mitigates electron shower damage, nor has anyone explained how mass transport or wafer exposure is handled, or how the supposed overlay of 1.6 nanometers was achieved. Now, industry veterans have seen this pattern before. The same claims, one of perfect alignment, tabletop sources, and a national mission, these all surfaced from the IBM and Bell Labs X-ray programs 40 years ago. Those projects produced beautiful single-layer micrographs, much like the ones we've seen from Substrate, but they failed on throughput. They failed on throughput, resist damage, and mask reliability. Substrate's promise of a sub-2 nanometer foundry by 2028, an amazing promise, replays that script almost verbatim, only with modern venture capital instead of corporate research funding. Then there's the human factor in all this. Substrate, as a company, lists no identifiable engineers on its website. No lithography veterans, no optics specialists, no known resist chemists, and no process engineers from existing fabs. At the time, I had to search through the California equivalent of Companies House to find that Proud is listed as a CEO, CFO, and other directorate positions. A lot of the employee listings on hiring websites appear to be AI generated as well. Proud in his interview speaks fluently about national strategy, but sparsely about stepper calibration, contamination control, or mask lifetime. The secrecy might be legitimate stealth, or it might be that the engineering team simply hasn't solved all of these yet for large-scale manufacturing. And one concern here is also credibility. It's been highlighted before in the press that Proud's last hardware company, Hello, collapsed despite enormous publicity and retail partnerships. It's a Kickstarter that took money from investors but failed to deliver, on time or with a competitive business proposition. Its core problem essentially was execution, not imagination. The parallels are striking though. It's a bold mission with glowing media coverage, but even basic details went unanswered and rapid scaling plans came before technical validation. The thing here is, even with all that, if Substrate succeeds, it could be transformative. Not just a new lithography system, but a rebirth of the American foundry model. But for now, the company's rhetoric outpaces its evidence. The promise rests on claims that contradict known physical limits, things like photon flux, shot noise, resist absorption, and power delivery. Until Substrate publishes measurable data, even a single full wafer exposure under controlled conditions, the only safe conclusion is that the physics, the economics, and the track record all remain unproven. It doesn't help that a lot of the coverage on Substrate so far has fallen into the mindset of what if rather than actually how did you. Now, to put this in context here, Substrate isn't just claiming to match existing tools, because the company is claiming to outperform ASML. That's a $400 billion company with over 3 decades of research, supply ecosystems, and metrology infrastructure built around EUV. ASML's current scanners represent the combined output of hundreds of companies and hundreds of thousands of research engineers across optics, materials, and precision engineering. For Substrate to exceed those metrics outright would imply that a single $100 million startup solved not just 1 or 2 bottlenecks, but the entire photonics, materials, and systems engineering stack simultaneously. They're also projecting that success for such an endeavor would mean a foundry that could eclipse TSMC's market capitalization on the back of a tool. Which tool? Well, that's for us to find out, it seems. So let's actually go back to the economics, just in case this really is synchrotron level. Let's put real numbers into the equations. We'll start from the dose needed to expose a wafer. For leading edge EUV, that's around 30 millijoules per square centimeter. Every wafer in the world at 5 or 3 nanometer gets that much light energy during a single exposure. For the wavelength of 13.5 nanometers, each EUV photon carries around 92 electron volts of energy. If you divide the dose, 30 millijoules per square centimeter, by that energy, and you put it across a full 300 millimeter wafer, you get 1.4 times 10 to the 18 photons per wafer. A machine that runs at 160 wafers per hour means that it takes 22.5 seconds per wafer. So that EUV machine is delivering on average 6.2 times 10 to the 16 photons per second. So let's jump over onto X-ray. Suppose we're using a 200 electron volt photon. It's a little over twice the energy of EUV. To deliver the same amount of energy to the full wafer, you need fewer photons. It's around 6 times 10 to the 17 photons per wafer. That's the number of photons that actually have to hit the photoresist on the wafer, the usable ones. In the real world, not every photon leaves the source that makes it there. If only half are absorbed in the resist, you need to double that count. If only 10% get absorbed, you need to multiply it by 10. X-rays tend to pass straight through most materials, so this isn't a small correction. It's actually part of the main problem. But we'll give X-ray the benefit of the doubt here for a moment. Now let's talk about how fast a typical synchrotron would actually supply those photons. A good soft X-ray beam line, such as the ones in the US or Spain, on a good day might produce around 10 to the 13 photons per second per beam line in the right wavelength range. In order to supply the photons needed to the wafer, we can do a simple calculation. That's 6 times 10 to the 17 photons per wafer divided by 1 times 10 to the 13 photons per second. That number, we get 60,000 seconds per wafer, or 1.44 wafers per day per beam line. This isn't even getting into the field size or scanning yet. That number's not good. Now we can get about 30 beam lines at that flux, so that means you can operate on 30 wafers at a time, assuming everything is perfectly efficient and scanning never stops. In total, that's 43.2 wafers per day. Now that's the optimistic case. If you drop the flux to an average photon flux, rather than the best case, that number is halved. This is before you add any overhead for wafer alignment, metrology, or resist development. On to the cost. This is big here. A large purpose-built synchrotron could drive 30 beam lines, and that would run around $450 million to build, depending on energy and design. I actually looked at published data for a variety of installations across US and Europe to come to that number, but also gave the assumption that we could pack as many beam lines in as densely as possible. Operating costs for the power, cryogenics, and beamline maintenance come to around $50 to $80 million a year. Now, these facilities often run for around 30 years, including a midlife upgrade. If you spread the CapEx and OpEx over that 30-year life to get TCO, running 24/7, that's roughly $11,000 per hour just to keep the light on. That's even before you expose a single wafer. Now, how can we combine that with the wafer throughput numbers? Even at 43 wafers per day, or 16.6 hours per wafer, that would come to a best case of $6,000 per wafer. Now, that sounds cheap compared to like the $25,000 per wafer we see today, but that's because it's not the same comparison. That $25,000 is multiple exposures from start to finish with foundry margin built in. Our $6,000 per wafer number is just running costs for a single exposure. Nothing about other layers, nothing about other tools. A modern wafer at TSMC will have 4 or more EUV exposures. Now, X-ray could reduce that down to 2 or 1, but $25,000 is still the all-in price, not the per layer price. Let's actually compute that per layer EUV price. A single ASML scanner, costing roughly $200 million, can expose around 160 to 200 wafers per hour every hour. Each wafer takes around 22 seconds, and the tool will run around 7 years. And based on estimate costs, that could be about $20 million a year on the high end for maintenance. Again, rough numbers here. A lifetime for the tool that costs $350 million over 7 years is around $6,000 per hour. That kind of sounds about the same, right? Well, no, because that's per hour, not per wafer. At 22.5 seconds per wafer, that cost is $37.50 per wafer. So it's $6,000 per wafer per layer exposure compared to $40 if we round up. On top of that, let's look at the tool installation economics. You can fit a dozen or more EUV tools in a clean room, each running in parallel. If you lose one tool to maintenance, the rest keep going. The synchrotron model, on the other hand, is centralized. One ring feeds every beamline, and if that ring goes down, every exposure station goes down. The footprint is hundreds of meters wide, and the power draw is in the tens of megawatts. You can't simply just buy another one and drop it next door. Now, in this video, we've covered a lot about the complexity of X-ray lithography, but even if the economics worked on paper, there are still practical physical problems. Each one could stop X-ray lithography before it ever gets close to a fab. Some of which I've already mentioned, but there are a couple more, but let's recap. Let's start with chemistry. The photoresists used in EUV today are the result of decades of tuning. They're designed to absorb 13.5 nanometer light just enough to trigger a clean chemical change without burning or scarring the surface. Each photon of EUV releases secondary electrons that help define the pattern, and that's what makes the reaction controllable. X-rays change that equation completely. At higher energies, or even higher energies, the energy density is so high that the resist just doesn't react, it breaks. As a result, you get damage, bubbles, and carbonization. One idea is to make the resist thicker or load it with heavy metals like tin or gold such that it can actually absorb more of that energy. But that immediately blurs the pattern because the light spreads deeper before stopping, and the electrons scatter further, something called the K-edge. The result isn't more precise, it's just fuzzier. And even if you had a magic resist that worked, you need new etch chemistry for the layers underneath. None of the current processes are designed to handle that kind of material or those energy levels. Then there's the tool chain. Semiconductor manufacturing is calibrated to visible or ultraviolet wavelengths. The optics, the stages, the sensors, and even the metrology tools all depend on photons that can be reflected, focused, or measured. There are entire industries that exist just to keep those systems clean and aligned. X-ray lithography would throw all of that away. You need new mirrors, new detectors, new alignment systems, and new inspection tools, and none of that infrastructure exists. I'm not saying it's impossible because we've done big changes before, but that infrastructure requires more buy-in from more people than ever before. An example of this would be moving to 18-inch wafers. The work has been done. It's been shown, and arguably it could drive chip costs down a lot more. The problem is, the tooling industry would have to change too. We're not talking just one company here, one company there. We're talking about the whole industry of research and approach. This would mean building 450 18-inch tools to go into the fab that already are running 300 millimeters. You're not talking about a few $100 million to change the industry. You're requiring $1 trillion over multiple decades to go push 450 millimeter or 18-inch wafers. It's simply just not possible with the way the current economics work. Now beyond that, we also have infrastructure and power. Now, a synchrotron isn't a piece of equipment you can just drop into a clean room if you're using one. It's a national facility. The buildings that these are housed in alone are measured in hundreds of meters. The vacuum systems, the shielding, the cryogenics, all of it consumes tens of megawatts continuously. You can't switch it off at night. The whole ring has to stay in equilibrium. Existing installations are part of the national fabric, and systems like ALS, ESRF, and Diamond each cost hundreds of millions just to build. Then they support a few dozen beamlines used for scientific experiments, not a production facility. There are also multi-year manufacturing projects, much like a modern fab, not something you can build in a few months. This is another angle which makes the 2028 promise from Substrate a little bit unrealistic. And this brings us to the part of Substrate's announcement that they actually try to address the scale of the capital needed to deliver this change. The entire company has raised around $100 million. That's not even enough to buy a single EUV tool, let alone build a synchrotron or staff a fab, or invent a new materials ecosystem from scratch. The kind of project they're describing would take the combined resources of ASML, TSMC, Intel, and the US government working in unison for a long time, maybe a decade, maybe more. Realistically, it's not a startup problem, it's a $1 trillion national program. The CEO has at least realised this and stated there's a 1% chance it'll work, but dresses that up in "Save America" rhetoric that becomes iconic of last-ditch attempts. Now sure, a few $1 trillion. With $1 trillion, I'm sure you could raise the Titanic, but that doesn't mean the money exists from people who would willingly invest, or they would be pledged on promise. What Substrate is describing only works if you can rebuild every layer of modern semiconductor manufacturing at once. And that's not just simply ambition. I'm not saying it's delusion either, but you need more to convince people than just rhetoric. So before you even reach the question of things like photon flux, you're already in implausible, if not impossible, territory. The chemistry doesn't exist, the tool chain doesn't exist, and the power budget doesn't exist, and the capital doesn't exist. It's not the setup for a breakthrough. It's kind of the definition of a red flag. So where does that leave us? In the space of a week, Substrate has gone from total obscurity to front page coverage across mainstream media. It was framed as a bold new challenger to the semiconductor establishment, a young founder taking on an industry of giants, promising to restore American leadership in the most advanced part of chip making. It's a perfect story for headlines, especially when it plays into the political moment. We're talking national security, supply chain control, and the idea that startups, not institutions, will fix everything. The thing is, the reality underneath that story doesn't match the scale of the claim. Substrate says it can do what no one, not IBM, not Intel, not ASML, not TSMC, not a single national lab, has ever achieved. They're saying they can turn X-ray lithography into a production process. They say they can build a new foundry from scratch, invent new chemistry, construct an accelerator campus, and do it all for a fraction of what one leading-edge fab costs. They claim numbers that outperform ASML, a $400 billion company with more than 3 decades of continuous research, and they suggest that will grow into a business larger than TSMC. That's not just blind optimism. Then there's the presentation, especially the one on the website. The website lists no technical staff. The clean room photos that we've seen look like a lab for small-scale metrology work, not a lithography floor. There are no conference papers. Still on the lookout for patents. There are no tool partners, no data, only images without scales, and a handful of press quotes. The media push was carefully staged, and it worked. Articles across so many mainstream media, Reuters, Bloomberg, Stratechery, SemiAnalysis, within 24-48 hours. Investors and journalists repeated the story because it fits a very particular narrative, that America could leapfrog its way back into chip dominance through innovation and willpower alone. So the thing is, my personal issue is, it's not about hope, it's about credibility. When a company releases performance numbers that beat the world's most advanced lithography tools, but offer no data, no publication trail, and no team, that's not stealth, it's just simply absence. Let's turn to the founder for a second. He's intelligent, articulate, and confident, but he's not a lithography engineer, and his record shows no experience in particle physics, material science, or semiconductor process development. Reports have shown that he's also registered a company related to fusion at the same address, and that his brother is the co-founder of both. And as far as I can tell, neither of them have degrees, let alone STEM backgrounds. Now, overall, it's just very frustrating. This industry thrives on optimism, but real progress comes from physics and data, not press releases. We've seen how long it took EUV to move from concept to production. Almost 40 years, thousands of engineers working together, billions of dollars, lots of academic publications, and honestly, there's still more to come. EUV is improving. If Substrate had real results, they should be the first to show them, not hide them behind patriotism and not offer them behind wavy hand economics. In the end, the story here isn't about whether X-ray lithography can ever work. It's about how easily the promise of breakthrough can eclipse the hard engineering that makes breakthroughs real. Until there's evidence and data, the only thing we can verify is the hype. And by the amount of calls I'm getting, they're all asking, is this even real? Now again, I'll reiterate, just before I started recording this, the founder did reach out and say, hey, let's have a chat, why not come for a visit? I'm going to take that call, I'm going to see if I can head over there relatively quickly, and we're going to see if this video deserves a follow-up. I'm sure that it does. I will try and get some data out of him, data that I can publish and share, because honestly, this needs to happen, right? If they're true to these claims, as SemiAnalysis says that there are, I need to see them. I need to see it in the people, I need to see it in the graphs, I need to see it in the data, I need to see it in the design. You don't overturn 50 to 100 years of lithography on its head with $100 million. And the fact that the response from the media has been like this really surprises me. I've lost a lot of confidence in a lot of people. for America!